Hello friends, this video on chemical bonding part 15 is brought to you by examfear.com. No more fear from exam. Before watching the video, please make sure that you have watched part 1 to part 14. Let's talk about polarity of bonds. So we told we have something called ionic bond, polar bonds, ionic bond, covalent bonds. So, but in reality, none of the bond is pure covalent or ionic. Only in theory we have pure covalent and ionic. I mean, sometimes we have, if you have same atoms to form molecule, we generally have, but most of the case we don't have pure covalent or ionic bond. So in case of covalent bond, we have ionic, right? For example, if you see that in case of water, H2O2, Cl2, N2, they have similar atoms, right? Then it is non-polar covalent bond. That means it's a pure covalent bond because they are all same, right? Both attract each other in the same degree. For example, H and H, there is no possibility of forming a partial charge. But it is something like HF, right? For example, HF, you have fluorine will attract electron all the more. So in that case, fluorine will get partial negative charge and hydrogen will get partial positive charge. Thus, this if you see, is called a polar covalent bond. And due to this polarization, we have something called dipole moment. And dipole moment is what? Product of magnitude of the charge and distance between the positive and negative charge. Product of charge magnitude into the distance. Unit is dB. So if you see the dipole moment, mu is nothing but charge into separation and the unit is dB I told. And please note it is a vector quantity and depicted by a small arrow with a tail on the positive center. For example, in this case, the tail is the positive center I told. This has a positive charge and this fluorine got a slightly negative charge because fluorine attracts electron more than hydrogen. So the electron wants to spend more time with fluorine than with hydrogen, and thus the fluorine gets partial negative charge, right? And this is a vector quantity where the positive, the tail is towards the positive and the head is towards negative charge. So dipole moment is a vector quantity, and this value is nothing but charge into distance, and this comes because of polarity of bond, because we have covalent bond which are polar. So because of the polar covalent bond, because this polar covalent bond exists in heteronuclear molecule, for example HF, HCl, right? So in a homonuclear molecule where the atoms are same, this polarity doesn't exist and they are called non-polar covalent bonds. But in case of heteronuclear molecules like HF, HCl, so I have a polar covalent bond, and when there is a polar covalent bond where you have partial charge on the atoms in the molecule, though the whole molecule is electrically neutral, but there are partial charge on the atoms in the molecules, and thus we have dipole. I think we have seen in the case of O3 also there were some partial charges on these atoms, right? So if you have partial charge on the atoms of a particular molecule, you have something called dipole moment. So the dipole moment, if you see, does not depend only on the individual dipole moment. So if you see, if this is the individual dipole moment, this is the individual dipole moment, but the whole dipole moment is not only the individual dipole moment. They are called bond dipoles, individual dipole, but on the whole thing. For example, I'm saying dipole moment, I told is a vector. So dipole moment of a molecule is vector sum of all the dipole moments in the various bond. For example, if you see in this case, my H2O, so I have this guy got positive charge, this guy got partial positive charge. Oxygen is more electronegative than hydrogen, so it will get partial negative charge. So if you see, there's a dipole here, there's a dipole here, and the net dipole is this guy. This is a net dipole. If you talk about BeF2, fluorine is more electronegative, so fluorine will get a slightly negative charge, and beryllium will get slightly positive charge. But if you see, this is my bond dipole, this is my bond dipole, but the net dipole is 0. There is no dipole. Why? Because both cancel each other. So vector addition of these two will be 0. If we talk about BF3, here fluorine will attract more. So fluorine will get partial negative charge, partial negative charge, partial negative charge. This guy will get partial positive charge, right? But in this case also, if you see, the net dipole will be 0. If you know physics a little bit, you see, if you take the cos of this, the angle is such a way that these two, cos of these two adds up to this, and sine of these two cancel each other, and thus the net dipole in this case also is 0, right? But in case of water, if you see, there is a dipole. So the point here I am trying to say is that the net dipole is my total vector sum of all the dipoles, correct? So there are some special case here. So if you see, this is NH3 and this is NF3. Now fluorine is more electronegative than hydrogen. So that means this guy has a lot of negative charge. But here in this case, nitrogen will get negative charge. Why? Because nitrogen is more electronegative than hydrogen. So the one which is more electronegative will get a negative charge. So in this case, this is negative, right? This is 3 times negative. This is negative, negative, negative. And this guy is, let's suppose, positive charge here. Here also it's positive, positive. Right? But here fluorine is very electronegative than hydrogen, and it forms bond dipole, right? So there are so many. This bond dipole is pretty strong, but in spite of this, the net dipole moment of NF3 is greater than NH3. Sorry, the net dipole moment of NH3 is greater than NF3. See, NH3 has greater dipole moment than NF3. Right? This guy is more. Why? Why do you think so? See, the individual dipole of this guy, NF3 is more because fluorine is more electronegative, right? But the net is of this guy is more. Why? The reason is pretty simple. See, in this case, NH3, if you see the dipole moment, the resultant comes in this direction, right? And the lone pair dipole moment is in this direction in both cases. Because there is a lone pair here, the lone pair, 2 electrons sitting here, right, in this. So in this case, this dipole which you are getting from these 3 NH dipole is adding to this dipole. But in this case, if you see, the net dipole is like this. These 3 are the dipole I am getting from NF3, and this dipole I am getting from this lone pair. So this is subtracting. So the dipole is less. But in this case, if you see, the net dipole I am getting is in this direction, plus this is my lone pair dipole. Everything is adding up. So that's why the net dipole, the resultant dipole in case of NH3 is much more than NF3. But if you talk about individual dipole, then NF3 is stronger. But the way it is arranged is, it is cancelling each other. So the dipole moment of individual bond matters, but the arrangement also matters, right? Because the arrangement, if you see, this guy has more dipole than this guy. NH3 has more dipole than NF3. But the fact is, this dipole strength is more than this dipole strength. But because of the arrangement, the whole thing changes. I'll explain once again. In case of NH3, my dipoles are like this. The NH3 dipole, NH dipole, and this is my dipole for lone pair. Everything is adding up. In this case, my NF3 dipole is in this direction, and my lone pair direction dipole is in this direction. So in this case, it's subtracting. Right? In this case, it is everything is adding up. In this case, it is cancelling. Correct? So, and please note, the resultant dipole in this case is in this direction, and the resultant dipole is in this direction. This is my resultant dipole, and this is my resultant dipole. Correct? Here in this case it is in this direction, and in this case it is this direction. Correct? Let's discuss covalent compounds characteristic. In ionic compound, we saw that they exist mostly in solid, but in this case, covalent compound, they exist in all three physical states. The crystal structure of this covalent compound consists of molecules actually in this case. They have low melting and boiling point because they are held by weak van der Waals force, and we'll explain this van der Waals force in the next chapter. They are soluble in organic compound and they are insoluble in polar solvents like water. Polar solvent, as I told, is something like this, where it has slightly positive charge and slightly negative charge. Right? So polar solvents like water, they are insoluble and they are bad conductor of electricity. And the reaction is very slow. Thank you. Visit examfear.com to watch free educational videos, try free online tests, get the best quality study materials, study from the best tutors and mentors, and much more. Thanks once again.